Hello, greetings of the day to all. I welcome you all to yet another doubt clearing or a sample problem solving session for the course Fundamentals of Electrical Engineering being taken by Professor Debapriya Das from IIT Kharagpur. I am Swastik Sharma and I am a PhD student at IIT Kanpur. So let me share my screen. Hmm. So last week we started first order circuits. So what do we mean by first order circuits? First order circuits are those circuits which result in, which while solving for the voltage or current relationship with time, we result in a different first order differential equation, right? So we discussed RC or RL source free circuits, and we solved some problems related to that, and we also went through some singularity functions. These were impulse function, unit step function, and ramp function. And we saw what was the relationship between all of them, right? So now we'll look at uh, s- source. Now we'll look at how the um, RC circuits or RL circuits respond to these to the step unit step function, right? So first we'll discuss is step response of an RC circuit. So we did look at this for a brief. We discussed one or two questions last week where there was a step response and we were required to find the voltage across the capacitor, and we saw how to solve them, but still we'll go through how to do the analysis or how to find out the step response of an RC circuit. Okay, let's say we have a voltage source which is ESU, right? ESUT. And there's a resistor connected to a switch S, a capacitor, let's say it was initially charged to some voltage V naught for time t less than 0, right? And there was this current. So at t equals to 0, we close the switch and then IT current flows through the circuit, right? So how would this VSUT would look like? For t less than 0, it's 0. For t greater than 0, it's Vs. Okay, because we are the unit step is being applied at time t equals to 0. Great. So and since it was charged initially, the capacitor, that means at 0 minus and 0 plus, the voltage is V naught that it was initially charged. So let's solve the circuit. Let's do loop. Let's do KVL across this whole circuit. It would come out to be VSU of t minus ITR and minus VC, right? Now, IT we know since it's a capacitor connected to this, so it's C dVC by dt, right? So this would become VSU of t minus C dVC RC dt minus VC equals to 0. Now we'll look at this equation for t greater than 0. Okay. So we know for t greater than 0, Vs ut is what? Vs. And this is Vs equal okay. Now we know how to solve the circuit. Let's do it quickly. So Vs minus Vc is equals to Rc dVc by dt. My words here. Which means it would become dt upon Rc. Yeah, dVc upon Vs minus Vc. Let's solve the circuit. It would be integrating from 0 to t and from V0 to some Vt, right? Because initially at t equals to 0, the capacitor voltage is V0. So this would become ln Vs minus Vc from 0 to Vt, which is equals to Rc t from 0 to t. It's nothing but ln Vs, sorry, not 0, it's minus Vt and Vs minus V0 is equals to TRC. Sorry, dt upon Rc, right? So it won't be TRC. T upon Rc, related to t, it would be T upon Rc. Now taking exponential both sides, so this will become Vs minus Vt equals to Vs minus V0 e raised to power t by Rc. There would be minus over here, right? Because Vs is here, so this would be minus. Minus would come here and this will be minus e raised to power. Because we are integrating with respect to Vc and Vc is with minus, so 1 upon L and dx upon ax plus b integration is nothing but 1 upon a ln kx plus b, right? So we did the same. We got Vs minus Vt, which means Vt is nothing but Vs minus of Vs minus V0 e to the power minus t by tau, right? Rc is time constant, which we can write as Vs plus V0 minus Vs e to the power minus t by tau. So that's how a step response to a capacitor will look like. So we solved it using, so we applied KVL. We knew current is nothing but C dVc by dt. And we solved the whole circuit for t greater than 0, integrated it, and we got the voltage across the capacitor uh, uh, to be this, right? This equation. Now, if you closely look at this, how can we write? This it can be written as VSS plus some transient, right? Where VSS is steady state voltage and TR is some transient voltage. Now, as our t tends to infinity, because it's a decaying exponential, the transient voltage decays to 0. And that's why the remaining term that we got, we call it as a steady state voltage, because it's a steady state function, right? This is the only term that will remain as a transient dies down. So now, if you can see, we can derive a very interesting conclusion that for any capacitor T, the equation of its voltage can be written as V of C at time tending to infinity, that is at steady state voltage, plus Vc at T naught at some starting time, minus again Vc at some time tending to infinity, which is a decaying exponential, right? The transient is a decaying exponential. So this is how we can write the voltage across capacitor quickly when we are solving something. Let me write it. So without even going through the pain of solving the circuit, solving the differential equation, we can straight away, as we have reached to this conclusion, seeing at the voltage of the capacitor, that it's nothing but uh, the uh, the summation of voltage at its steady state plus the summation of plus the voltage at the plus the transient voltage, which is a decaying exponential. One more conclusion can be derived, which is VCT is nothing but the natural response of the circuit plus the forced response. Now, when we solved, so do you remember? So, if you remember, when we were solving this source-free circuits, so what was happening to the capacitor voltage? It was decaying exponentially to zero, right? So that was its natural response, V naught e to the power minus t by tau. Now let's say uh, if the now when we solved it for the independent for the sources connected to the capacitor the last time, we got Vs 1 minus e raised to power minus t by tau. If you go ahead and watch my previous lecture, you will see that we derived both of these terms independently for a source-free RL circuit and with a source circuit, right? So if you see, it can be written as Vs plus V naught minus Vs e to the power minus t by tau, right? So this is one more interesting conclusion, that if you don't know how to solve a circuit, you can simply find the natural response, that is remove the source, see how the capacitor will die, decay to zero, how the capacitor voltage will die, and see the forced response, that it was, let's say it wasn't charged initially, and if you just simply gave it a voltage Vs, how would the capacitor voltage look? So this is how you solve for the source step response of an RC circuit. We'll quickly do the current response as well. Then we'll solve some sample problems which are essential for you to know if you want to solve the week 7 assignment. Hmm. Let's see how the current response will look. We have a current, let's say IS. We're still looking the step response. Oh, sorry. Step response of an RC circuit with current source. Hmm. So there would be a resistance in parallel with it and a capacitor, right? Let's say it was initially charged to some voltage V naught, and Is can be represented as, for t less than 0 it's 0, and for t greater than 0 it's capital Is, right? Now we want to see how the step response for a current source would look like for this RC circuit. So let's see. Again, as I told you, we'll just simply use the formula that I just provided. Okay. Now what is tau here? Tau is nothing but the equivalent resistance to the equivalent capacitance as seen from the capacitive side. So it's nothing but RC, right? And what is VC at infinity? So at t tending to infinity, the capacitor would charge, and once it charges, it would become an open circuit, right? So if it becomes an open circuit, let's see, as t tends to infinity, this is how the circuit would look. IS, resistance, and there's an open circuit, VC. So what is VC here? VC is just ISR, right? The current is directly flowing through the resistance, and whatever the voltage across it is the voltage of the capacitor. So VC as t tends to infinity is ISR. Now VC at 0 minus is nothing but V naught. Since capacitor cannot change its voltage abruptly, we know that VC 0 plus will also be V naught. So now there's nothing there. We just need to add this to that equation, and what will we have? We'll have ISR plus V naught minus ISR E minus T by tau, which, yeah. So for a current source, for a step, what you can say, step current source, that's how the this capacitor voltage will look like. Okay, let's do step response for an RL circuit, and then we'll start question. It's visible, right? So we'll see step response of an RL circuit. So again, we have a voltage source connected across a resistance. There's a switch S which is closed at t equals to 0. So there's a resistance, an inductor with inductance L. And let's say initially there was a current flowing in it, and it was, let's say it was there was an external circuitry and there was a current flowing through it, which was I naught, right? And this is the current that flows after t to t is 0. So let's write KVL. So for t greater than 0, right? So we know for t greater than 0, VSUT is just Vs. It's a step response for t greater than 0. And then we have ITR minus VL equals to 0. This minus ITR minus LDIL by dt equals to 0. So now there are two ways to solve this circuit. Again, the same thing that we used for capacitor over here, we can use the same thing for inductor. But what we'll do is we'll solve this whole equation so that you get a feel of how this whole step response comes into picture, right? So let's do it. So LD by dt, let's call it IT only. So it's convenient. Plus equals to Vs minus ITR, right? Now we'll just take this over here. DIT by Vs minus ITR equals to dt by L. So again, we know we are solving for t greater than 0, right? We'll integrate it from t equals to 0 to t, where the current was, let's say, some I naught, and it's I of t. So again, minus ln Vs minus ITR, and since it could be divided by R, from I naught to IT. Please feel free to interrupt if you have any questions. 1 upon L, sorry, T upon L, 0 to T. Let's equate this would be ln Vs minus I of t R So taking exponential both sides, we'll get Vs minus. Okay, so let's rewrite this whole equation. It will become Vs. So this is how the equation comes up to be. Let's rewrite it so that this is plus. So this would become I naught minus Vs by R, right? So let's again look at it. So this would also be I in steady state plus I some transient, right? So this thing is steady state current and this is transient. Let's see. So when t tends to infinity, the inductor will short itself, right? So once inductor shorts, what is the value of IT? IT is nothing but Vs upon R. So the steady state value is Vs upon R, and the transient value is the current at time t equals to 0 minus current at time t equals to infinity times an exponentially decaying function, right? So that's how step response of an RL circuit and an RC circuit is calculated. So as you can see, it's nothing but what we solved is we used differential equations. We made we integrated them. We integrated them after, of course, doing some analysis. We integrated them, and we found out to write it. We don't need to solve the whole circuit. In fact, we can just simply say that for an inductor, the current is nothing at time t is nothing but I of infinity plus I at time t naught. T naught was zero here. T naught was zero here, but still at time t equals to t naught. If you close the switch at t equals to t naught, what would come here is t naught only. So time minus I infinity minus e t by tau. Of course, tau being L by R. So that's how you can write the equation for current for a for an RL circuit if you're trying to solve it. So any questions till now? Any questions? Okay, since there are no questions, we'll move ahead. So let's solve sample problems. For week 7. So let's solve this first question. It's a clear. Yeah, hope it's clear. So it's saying initially the circuit was relaxed. That means relaxed circuit means there was no the circuit wasn't energized by any means, right? So that means ILT was 0. So if ILT, so IL for 0 negative was 0, that means it's true for IL for 0 positive, since the inductor does not um, cannot change current abruptly. Okay. So so we have to determine the value of IT at t equals to 2 seconds. What we're given here is we have a voltage which is a ramp function for t, and it's supplying an RL circuit where R is 2 ohm and L is 4 henries, right? And we have to find t equals to 2 seconds. So how can we solve this? So again, here we can't make use of the fact about steady state, because this circuit won't be in steady state, as the voltage is a function of time t. So we have to solve it through the conventional way. That's why I was I was teaching you how to solve a circuit in a conventional way. Let's do KVL. So what we have is 4t minus 2it minus VLT, right? Equal to 0. Where the VL is nothing but LD IT by dt, right? So let's equate. This would become 4t minus 2it minus L is 4. This is dit by dt, which is equal to 0. Now let's rewrite this whole thing. This would become 2 dit by dt plus 2. Sorry, it's 2 will get cancelled. It equals to 2t, right? Which can be written as dit by dt plus half. So now to solve this differential equation, there are two methods. One is Laplace transform. We can transform this whole equation from time domain to frequency domain or S domain. But since there are many of you who are from the first year of in the first year of engineering, we will not solve it using that concept. What we'll use is the normally how we solve a differential equation, right? So now this differential equation is in the form of dy by dx plus a with ay b times x, right? So this is in the form of where x is t and ax is equals to half, right? It's a constant. There's the a is not dependent on. Let's write it like this: dy by dt at into bt, right? Now, to solve this circuit, there is a concept of integrating factor. So this integrating factor is nothing but e to the power integration of at dt, right? So that's how we are going to solve this differential equation using this integrating factor. Let's see what the integrating factor for our equation would look like. At is half dt, which is nothing but e to the power t by 2. Okay, so we'll use this integrating factor and multiply both sides to this equation. So don't worry if you don't know. So you must be going through differential equations and how to solve them in your first year of first year of studies for the mathematics based classes, and you'll know how to solve these differential equations. So, and all of the other people who are not in the first year or who have completed the first year are familiar with this concept. That's why I'll be teaching you this. So if you multiply both sides, how will it look? It would be e to the power t by 2 dit by dt plus half e to the power t by 2 it equals to e to the power t by 2 t. So if you see this left hand side, you'll see it's nothing but uh, chain rule differentiation of e to the power t by 2 into it, right? It can be written as d by dt of e to the power t by 2 it, right? Chain rule. So we take et by 2 as constant, differentiate it, then take it as constant and differentiate e to the power t by 2. So we make use of that fact and we rewrite this whole equation. This would become now what we'll do is, so we'll integrate, right? Now it's straightforward. If you see, let's integrate e to the power t by 2 it dt, right? So now This is how the equation looks now. So let's solve the right hand side. Let's take t by 2 as x. That therefore dx is half dt, right? So let's equate it over there. This would become 2 e to the power x. So sorry. So t would be 2x, right? So this would be 4x. And what's the formula for solving e to the power x into x dx? It's nothing but e to the power x minus e to the power, yes, e to the power x into x minus e to the power x. So it would be e to the power x into x minus e to the power x. Since it's an indefinite integral, we'll add a constant. So this is how the right hand side will look like. Let's equate it back. So x is nothing but t by 2 into t by 2 minus e to the power t by 2 plus c. Right? Now I write the equation back. E to the power, which means it is nothing but 4 e to the power t by 2. We can cancel. And here we can write minus t by 2, right? Now we know at t equals to 0, it is 0. So c would become, sorry, minus 4 plus c. So c is nothing but 4, right? Equating it back, it is nothing but 4t by 2 minus 4. So this is how the equation for the current will look like. So we got this, right? Now our main aim was to solve for t. So it for t equals to 2. Let's solve it at t equals to 2 seconds. So this is 0 plus 4e minus 1. So can somebody, so it's 1.472 amperes. Not 2, it's 4.1715, right? So yeah. So the answer is B, right? So that's how you solve if there is a differential equation with of this form. So I used nothing but the same how to use the differential equation formula. I formed an integrating factor which made the equation a bit easier by making it in the form of a chain rule. Then we integrated both sides, got this function for it, this function for it, and we were able to solve for t equals to 2 seconds. Now let's do another question. This time you will tell me the answer. Okay, it's the same circuit. Yeah, it's the same circuit, and we are required to find voltage at t equals to 4 seconds. Great. So VL is what? So VLT is what? LdIT by dt, right? We got the equation of IT. Here is this equation. 4 times t by 2 minus 1 plus 4 times e raised to power minus t by 2. Right? So let's see. So it would be 4. And 4t by 2 is nothing but 1 by 2, right? So let's do a chain rule instead of 1. It will be 16. T by 2 is 1 by 2 minus 1 is 0 plus 4 I took outside. It would be. So you can solve it and check with me if you are getting the correct answer. So 4 I took outside, it would be minus 1 by 2. E raised to power minus t by 2, right? So it would be nothing but 8, 1 minus e raised to the power minus t by 2. Let's solve. We require point for VL equals to 4. It would be 8, 1 minus e to the power minus. So I got 6.917 volts. So you can check if you're getting the same answer. And the correct answer is A. So if anyone has any problem till now, let me know. Then only we'll move ahead. Okay, since there are no questions, I'll move ahead. Third question. Let's solve third question. So what's given over here is a current source is supplying 15 ampere to the circuit shown in figure 3. The switch S, which is initially closed for a sufficient long time, is suddenly opened. Obtain the time response of the inductor current. Okay. So since S was closed for a very long time, let's see that S was closed at t equals to, oh yeah, S was opened at t equals to 0, right? Even if it was closed, no current was flowing through IL. That means IL 0 minus, which was 0, which is equals to IL 0 plus, right? Hmm. Now it's saying to find the current response. So as I told you, it's not, we can simply, instead of solving the whole equation, we can simply make use of the fact that we can write it using the shortcut I provided you earlier. It's nothing but infinity plus I 0 minus I infinity e raised to power minus t by tau. What is tau here? It's L by R. L is 3, R is 6, and this is 1 by 2, 0.5 over here. So how now let's solve for I at infinity. Now, for a sufficiently long time, what would happen? The inductor will short circuit itself, right? Inductor will become shorted if t tends to infinite. So the circuit would become something like this. So that means since it's a short circuit, what would happen? No current would flow from flow through the resistance at R, right? So all of the current will flow through the inductive path. So that means I infinite that I as time tends to infinite is nothing but 15 ampere at steady state. That means, and I zero we already talked. It's 0, right? So this would be 15 0 minus 15 e to the power minus t by 0.5, which is 15 1 minus e to the power minus t by 0.5. So what's the correct answer? It's C, right? 0.5, 1 upon 0.5 is 2. So C is the correct option. So any troubles for this question? Anything that bothers you, or is the pace fine? Is the pace too fast? I need something to move. Please make sure to go through my previous video, or if you don't want to go through the previous video, please make sure that you have watched the whole week 6 lectures before you attempt this week's problems, because if you haven't, you won't be able to solve these problems, and you won't know how to solve them. So please go through them. I mean, the shortcut is there, right? You can always use it, but if you don't have the intuition of how to solve these equations, you won't feel how the answers are coming, right? So let's move to fourth question. Okay. So it's saying in the circuit which S1 is initially closed and S2 is open. Okay, the inductor L carries a current of 12 ampere and the capacitor is charged to 10 volts. As indicated, S2 is closed at t equals to minus 0 and S1 is opened at t equals to 0. The current through C and the voltage across L at t equals to 0 plus. Okay, let's solve it. So, since capacitor voltage can't change abruptly, whatever was there before t less than 0 is there just after t greater than 0. And similarly, the current through the inductor can't change abruptly. Same notion would follow, right? Okay, so what's it saying? Now we have to find. Okay, so let's redraw the circuit. After the circuit is closed, what would happen? So that's so this is R1, this is L, switch S2 is closed, R2. So it's so let's find first VL. So how can we find VL? We'll use this we'll use KCL at this point A. So KCL at A. So if we write KCL, let's call this voltage would be VL, right? So this would be VL by R1, and the current is coming 12 amperes over here. So this is the current going through this node, from this node is VL upon R1. There's a current of 12 ampere coming, and the current going out of this loop, this node to the capacitor is VL minus of minus 10, that would be 10 upon R2, which would be equal to 0. So what is VL? VL, we can find minus 12, 10, R2 is 10, VL upon 5 minus 12 plus 1 equals to 0. So VL is 55 volts. So is there any option with VL 55 volts? Yeah, there is. There's only one option. D is correct that we know. So let's still find what is the current through capacitor. So what is capacitor current? This is the current that will flow through the capacitor, right? This is IC only. IC, right? So let's equate VL in this. So what is VL? 55 plus 10. R2 is 10, is nothing but IC, which means IC is 6.5 ampere. pretty neat, right? So that's how you solve this circuit. So we did nothing. We just took whatever the information was given, and we applied circuit analysis, right? And we found what was the right answers. Okay, just right. So t equals to 0 plus the right thing. So this is only valid for t equals to 0 plus. Just remember, right? So any doubts? Yes or no would be fine if you yes or no. I'm audible, right? Yeah. So let's move ahead then. So fifth question, let's solve. So what are we given? So we are given a figure where the ideal switch has been open for a long time. Okay. If it is closed at t equals to 0, then the magnitude of current through the 4 kilo ohm resistance at t equals to 0 plus is. Okay. Hmm. So since it is at a steady state for a very long time, right? Circuit was at steady state for t less than 0. Let's redraw the circuit for t equal to 0. So let's redraw the circuit. Since it was at steady state, what would happen to the capacitor? It would be open circuited and the inductor would be short circuited. Let's redraw. S1 is closed. Let's see when the S1 was open. Okay. 0 minus. Yeah. So this. So instead of 0 plus, I should have wrote 0 minus. So yeah, it's the same thing, right? For t equals to 0 minus, whatever the voltage was for the capacitor will remain same at t equals to 0 plus. It's just the fact that the switch wasn't closed at t equals to 0 minus. So this is switch S1. Now, can you tell me how much? So whatever current was flowing through IT, that is 4 kilo ohm resistor, was the same as IL, right? So what is IT? IT was 10 volts divided by 5 kilo 4 plus 1 plus 5, 10 kilo ohm resistance, right? So this is what? 1 milliampere, right? Okay, so we found out that the current was 1 milliampere. So that means IL 0 minus, what was it? it was also 1 milliampere, right? And what was VC? Let's see, VC at 0 minus was 10 minus 5 into 1, right? So it was 5 volt. So we got all of this. Now, when switch S1 now after S1 is closed at t equals to 0, redrawing circuit, right? So we can redraw the circuit again. So let's copy this circuit. Just a second. Yeah. Let's finish this question. So yeah, S1 was closed now. So, so this is our resistance. This is a capacitor. Now IL at 0 plus would be the same, right? So IL we found out was 1 milliampere. This would be 1 milliampere, and VC was 5 volts, and this would be still 5 volt. So we know at this point the current is going here, and it's nothing but IL, which is 1 milliampere. So finding this would be easy now, right? So this is 5. So so how can we find the value of IT? There are two ways, right? Either you can use KCL or you can simply use KVL, right? It would mean the same thing, right? So if we do KVL, I, so T0 plus, right? We are required to find I0 plus into 4 kilo ohm is nothing but 5 volts. So I0 plus is what? 5 by 4, which is 1.25 milliampere. Is this correct? Is this correct? So what we did, we drew the circuit for t equals to t just before, so just before t equals to 0, that is t equals to 0 minus. And we drew the circuit and we found the values of VC 0 minus and IL 0 minus, right? Now we redrew the circuit for S1 closed at t equals to, for t equals to 0 plus, that is just after the switch was closed. And since the voltage for the capacitor will remain the same and the current through the inductor will remain the same, we're trying to find what would be the value of current through the 4 kilo ohm resistance, and it's nothing but 5 by 4, right? Any issues, any doubts? Let me know. Just a moment. I'll, I'll be back. In the meantime, you can just look at this and let me know. Hello. Yeah, sorry to keep you all waiting. So, so if there are no doubts, let's continue to the next question. So what we are given here is a figure where it's a very big figure. It's so yeah, the circuit was in position one. That means the switch was in position one for a long time, and is then moved to position two at t equals to 0. We need to determine VC just after the switch was closed and IL just after the switch was closed. Okay, let's see. So let's redraw the circuit again. T. Right, so it was in position one for a long time. That means the capacitor and the inductor, the capacitor voltage and the inductor current reached a steady state. So we can rewrite it to become, so there's a 6-volt battery to a 25 kilo ohm resistance, then 20 kilo ohm resistance. Since it was connected for a very long time, that means this inductor would have reached its steady state. That means it was short circuited. And there's one more resistance, which is 50 kilo ohm, right? Since it was at switch one, and the capacitor would have been open, right? So this is IL1 and this is VC. There are two inductors and one capacitor. So, and denoting the first inductor by 5 Henry inductor by IL1 and the 4 Henry inductor by IL2, and the capacitor voltage we are representing by VC1 or simply VC. And the other circuit was disconnected from that circuit. This would be like this. Since it's T which is less than 0, if you see this, what does it show? It shows that here on that for T less than 0, the voltage was 10. In T greater than 0, it became 0. Remember this sign, minus T. It shows that for negative value of T, the voltage was 10, and for the positive value of T, the voltage is 0. Step response, right? We just removed that. We removed the step. Okay, since it was connected, that means we need to draw it. So it's a 10 volt voltage source, 1 kilo ohm resistance. Call it IL2. Okay, now, so what is IL1? So the circuit is like this, right? The current will flow from this, this, and this. So the total resistance coming onto its path is 75 kilo ohm. 6 upon 75 kilo ohm. 20 kilo ohm is because 20 kilo ohm is shorted. So it's 8 into 10 raised to the power minus 5, 80 microamperes. 8 into 10 raised to the power minus 5 can be written as 80 into 10 raised to the power minus 6. 10 raised to the power minus 6 is micro. And what would be the value of VC? VC is nothing but the voltage across the 50 kilo ohm resistance, right? So it's IL1 multiplied by 50 kilo. So how much is it? 4 volts. Great. So as you're seeing, when we are solving this equation, we are just trying to solve it at that point. Let's say here t equals to 0 when the switch was closed. We are just trying to find what happened before that, because that will determine that will have an effect on what happens after t equals to 0 or after the switch is closed. Right. So we got the following. Hmm. Right. Let's calculate IL2. So what is IL2? Since for a very long time it was shorted, right? IL2 is nothing but 10 upon 1 kilo ohm. So what was it? What is it? 0.01 ampere. Right. So we got all of the equations that we wanted. So what are we required to find? We are required to find, oh, we're not required to find anything else. So the answer is C, right? No. It's not 0.01 milliampere. It's 0.01 ampere. Right? This is the correct answer. Let me see. Yeah. Just a second. Yeah. Okay. So, so you're getting the feel of it, right? We are just trying to find what happened before the circuit was closed, and we're trying to find out the current and the voltages across the inductor and capacitor respectively. So, any doubts till now? I'm sure you'll be finding this very easy. This whole exercise is very easy. Any doubts? Sorry, it's indefinite integral with this C2. Let's solve another question. Okay, moving ahead. Let's take this into the next page instead. Hmm. It's visible, right? Hmm. So let's see. In the circuit of figure, the switch S has remained open for a long time. Okay. The switch closes instantaneously at t equals to 0. Determine V naught at t equals to 15 microseconds. Okay. Let's see at t greater than 0, what is tau? the time constant. So we'll see if the circuit has reached its steady state or not. So how do you find uh, uh, um, tau? Tau is 1 upon RTH. Sorry. For an RC circuit, it's nothing but RTH C, right? The Thevenin equivalent across that capacitor, and we'll find it, right? So what is the Thevenin equivalent across this capacitor? We'll switch off the independent sources. So let's redraw. It would be 10 ohm. The voltage source will be shorted. So trying to find it from here. There's a 5 ohm and a 12 ohm, which is open. So RTH is nothing but 10 in parallel with 5, right? So can anyone tell me what's 10 parallel to 5? It's 3.33 ohm. So that means the tau came out to be 3.33 into 2.5 microfarad seconds, which is 8.33 microseconds. Now 5 tau is equals to what? 41.67 microseconds. So since so the t 15 microseconds is less than 41.67 microsecond, that means circuit has not reached it steady state. Right, the circuit has not reached its steady state yet. So what we need to do is we need to solve it using the old way. And let's do it. So we know for a capacitor VCT, how do we write the voltage? VC infinity plus VC0 minus VC infinity. So let's find its steady state. So at steady state, what would happen? The capacitor will become open circuited, right? And 25 and 10. So we need to find VC infinity across this node. So let's do KVL, right? KCL at this node. So it's nothing. These two nodes are clubbed, right? So this whole node is one single node. So A, KCL at A, it's nothing but VC infinity minus 25 divided by 10 plus VC infinity by 5 plus, so minus 2, right? Since current is entering that terminal. So this would be 3 VC by 10 minus 2.5 minus 2 equals to 0. VC infinity is 4.5. 4.5 and 10 would be 45 by 3, which is 15 volts. So you got the value of VC infinity. For VC0. Now the switch S was open for a very long time, right? That means the capacitor was connected to this current source independently, right? So let's see what. Hmm. So redrawing the circuit for t equals to 0 minus, which is nothing but this was open. There was no 5 ohm, 12 ohm, I believe, and 2 ampere. Right? This was the case, yeah. So what is the value of VC0 minus? Can anyone tell me? It's straightforward, right? It's whatever the voltage is across that 5 ohm resistance. It's nothing, it's 10 volt, right? So VC is 10 volt. So therefore, VC0 minus is equals to 10 is equals to VC. So let's equate it in this equation. All of these values will get VCT equals to 15 plus 10 minus 15 e to the power minus t by 8.333. Right? Tau was 8.333. Which is nothing but 15 minus 5 e to the power minus t by 8.333. 8.333 microseconds. So don't forget this is necessary. Volts. Right. So now we need to find it at 15 microsecond. Micros and micros we could cancel. This is 5. So what is the answer? 14.17 volts. Did anyone get this? The answer is B. So any doubts? Straightforward, right? So why did we check in the first place for if the capacitor was in steady state or not? Had it been at the steady state, we wouldn't have required to find the voltage in the form of time, voltage relation with time, because if it was in steady state, it would have simply been an open circuit, and we could have calculated. It would have simply been 15 volts. But since it's not, we drew everything and we got 14.17 volts. Any questions? Okay, let's move ahead since there are no questions. So what's given in this question? We need to obtain an expression for IT, which is the current flowing through that 40 ohm resistance. For t greater than 0, the circuit was initially relaxed and the switch S has been closed at t equals to 0. Okay, so if it was initially relaxed, what does that mean? There was no energization performed. So all the energization was performed at t equals to 0. So that means for this for this inductor, the current at 0 minus was 0, which is true for 0 plus as well, right? Now we need to find the expression for IT. So let's do one thing. Let's find the expression for IL and then we can find the expression for IT too, right? Why? Because whatever the voltage is here, VL, IT is nothing but, sorry, I shouldn't present IT is that. IT is nothing but VL by 40, right? That's what it is. So let's find what's the equation for voltage over there. For that, we need to find the equation of current too, right? So let's do it. So equation of current through the inductor, we went through it too many times. It's the steady state value, that is this transient, that is this e to the power minus t by tau. Now what is tau? Tau is equals to L by R, which is nothing but, since if we open the circuit and close it, 40 and 30 are in parallel, right? Let's redraw the circuit. So this is 30 ohm resistance. It's connected across. This would be open because independent sources are switched off. Switches is connected. This would be opened. Then there's a 40 ohm resistance. And then we have this. So what is RTH? It's the parallel of 30 and 40 ohm. Parallel combination of 30 and 40 ohm. What is that? It's 30 into 40 divided by 30 plus 50, which is 120 by 7. So that means tau is equals to L by R. L is what, 30, right? So what is that? 7 by 4. Okay, so we got tau. Now at steady state, so we know IL0 is 0, right? So we didn't need to find it. Now let's find it steady state. At steady state, what would happen at steady state? Can anyone tell me? We've been doing this exercise for too many questions, right? So what would be the how would the steady state form of inductor look like? It would be short circuited, right? Yeah. So let's redraw it. The same question. So this is shorted. And there are two current sources, 100 and 200 ml each. Okay. Now, what is the amount of current flowing through here? Can anyone tell me? What is the current flowing through IL? Okay, how can we find what current is flowing through inductor? Anyone? It's straightforward, right? Okay, can anyone tell me, will any current flow through any of these resistors? No, right? Because the current sources are shorted. They will find a path of minimum resistance, and the minimum resistance path for this is just this circuit, right? So that means IL infinity is equals to 100 milliampere plus 200 milliampere, which is nothing but 300 milliampere, which is 0.3 amperes. Okay, now we have everything. So we can just straightforward write the equation. IT is 0.3 plus 0 minus 0.3 e to the power minus t by tau, which is 0.3, 1 minus e to the power minus t by tau. Very good. So we got this equation. Now what is VL? So what now we need to find VL, right? To find IT, we need to find VL. V I should divide it by ILT, right? It's confusing, yeah. So VL is LTIL by dt. So let's do L is what? 30 Henry, right? I suppose. Yeah. So d by dt of, so this is 30.30 plus 1 upon tau e to the power minus t by tau. Right? This would be what? 9 upon tau e to the power minus t by tau. Which means IT is VL upon 40. So 9 upon 40 tau e to the power minus t by tau. So we got all of the things, right? It's not 90, it's 9 upon 40. So what is tau? We found tau to be 1.7 by 4, right? So let's write. Let's 0.1286 e to the power minus 0.571 t. So we found IT equals to, this is what IT is. Let's match. 0.18 minus t upon 1.75. So 7 by 4 can be written as 1.75, right? So this is the correct answer, C. So any doubts? So we were required to find the current through the 40 ohm resistance. So what we can do is we can find IL, and from that we can ascertain the voltage across that inductor, which is LdI by dt, and equate that voltage because it's connected in parallel to that. So voltage will be same, and IT is nothing but VL upon 40. So we got the value of IT. So any doubts till now, up until this point? Any doubts? Or we can continue. Okay, let's continue then. Last question. Sorry. So I'll ask you to solve this question with me so we can match both of our answers. So it's saying to determine the VC for t equals to 0.8 second when the switch was closed at t equals to 0.3 second. Okay. And we are given a step voltage source 10 ut. Okay, let's see. So by now I've told this several times. For t less than 0, this was 0. For t greater than 0, it was 10 volts, right? And at 0.3 second, this voltage, this sorry, what am I doing? Yeah, this T was closed, right? So we can divide this whole thing now. Let's first see up to, let's first solve for t equals to 0 to t equals to 0.3 seconds. Let's first solve for this duration. So what happened to the circuit at until t equals to 0.3 seconds, we need to know so that we can find what is happening to the circuit at t equals to 0.8. Right. So as I told you, at t equals to 0, this was 10. Then there was an 8 ohm resistance connected to a capacitor of 0.05 farad. Right. So what is tau for this? Can anyone tell me? Tau. Tau is 0.4 second, right? So that means till t equals to 0.3 second, the circuit hasn't reached its steady state value. But still, let's find out what is the value of VCT. So we know it's nothing but at steady state plus initial minus steady state e to the power minus t by tau. Now, what is the steady state value? It's simply the voltage source itself. And initial value, since the voltage source was applied after it passed t equals to 0, that means it wasn't energized before. So it's 0 minus 10 e to the power minus t by 0.4, right? So this is what 10 1 minus e to the power minus t by 0.4. So this equation is valid till t, sorry, for 0 is less than equal to t is less than equal to 0.3, right? So this equation is valid till then. Now, when the switch was closed at t equals to 0.8 second, let's again find from t equals to 0.3 second, t equals to 0.8 second. What is happening to the circuit? So the voltage source is 10 connected with the resistance. Of resistance and continuous. Right. So now to write the value of VCT, what do we have to do? It's nothing but VC to infinity at steady state plus VC at T naught. Remember T naught, because the switch was closed, the circuit was like this when the switch was closed. And the switch was closed at 0.3 seconds. Yeah. So minus infinity minus T by tau. Right? So that's how the circuit will, so that's how the circuital equation would look. sorry. Um, hmm. So where was I? Yeah. Hmm. Now this won't be t by tau, right? It would be t minus t naught by tau because the circuit was closed at t naught, right? So that's how the equation would look like now. Any doubts up until this point? No, right? So I missed this point earlier as well when I was doing a question. Now I think I have to correct myself. Yeah. So when I wrote this IT naught, here also a T naught should come. Just remember, it's a rookie mistake. Because it's dependent on the when the circuit was came into that picture. The circuit so till that time from t equals to t naught, right? So the integral would be from t naught to t. That's how t minus t naught would come over here too. Hmm. Right. Anywhere else written? No. Only here as well. It could be t minus t naught right now. Because this integral over here, where did it go? Yeah. This integral would not be from 0 to t, then it would be from t naught to t, right? So since t naught I've taken as 0, I'm simply equating it from 0. But if you write for the equation for t naught, here this t minus t naught would come. While solving this equation, it came to my mind. Yeah, so we got this. Now we know what is VC at infinite. So we need to find VC at t tending to infinite. So this is 10 volt, this is 8 ohms. This would be open circuited. This is 4 ohm, 20 volt. So the current would be flowing here. It would be, so this current I would be 20 minus 10 upon 12, right? So 10 by 12, which is approximately 0.833. Therefore, this VC would be using this KVL over here, plus minus, plus minus. So this would be 10 plus 8 into 0.833, right? So VC would be 16.67. So you got this 16.67. Now what is VC at T naught, which is 0.3? So this would follow, right? Because it can't change it abruptly, and just before 0.3, whatever the value of VCT was would come from this equation over here, this equation. It would come from this equation, right? So let's write. So it's 10, 1 minus e to the power minus 0.3 by 0.4. Let's solve it. Bit 10. It's 5.276 volts. So what does that mean? At VC at T would be, this is, so what is this? This is 16.67 plus 5.276 minus 16.67 e to the power minus t by tau. Oh, sorry, t minus t naught. T minus t naught by tau. T naught is 0.3. So we found everything apart from one thing. What is tau? So we'll find Thevenin resistance across the capacitor, which means 8 and 4 are in parallel. So 8 into 4 divided by 12, which is 8 by 3. So let's solve this. This would be 16.67 plus great. So you got all of it right. Now just one thing remains. Put t equals to 0.8. Can anyone solve this for me? Let's see if you can get the answer right. Oh, sorry, this is R Thevenin, right? We need to multiply it with capacitor to about. So 8 by 3 into 0.05, this is 2 by 5. Sorry, 2 by 15. Yeah. So put tau equals to 2 by 15 here instead of 8 by 3. Now tell me if you got the correct answer. I'll also do it side by side. Anyone? Anyone who's solving, let me know. So it shouldn't be like I'm the only one solving this equation. Okay, since it's getting in, so it's 6.4 volts I'm getting. So let me know if you got the same answer. So see, because 6.3, right? It's 6.4, right? So if you solve it, you'll get it. So So any doubts for this question up until now? So it was pretty easy, right? Whatever we did, we started from checking the what was the value of capacitor from t equals to 0 to t equals to 0.3 seconds. Because once the switch was closed, whatever the value was, we needed it for that next equation, right? So we found it. We got 10 raised to power 10 for 1 minus e raised to power minus t upon 0.4. Now, hmm, just a second. Yeah, it was 0.527, just making sure it was correct. So we got that. Then we checked for what would be the circuit what would the circuit look like for t greater than 0.3 seconds, right? So because we needed that what would happen at 0.8 seconds. So we found that after the switch was closed, the circuit would look something like this. And then we found what the value of tau was. The time constant came out to be 2 by 15. Then we solved for the voltage equation for the capacitor, and we checked for the steady state value, redrew the circuit, found it to be 16.67. And we knew that at t equals to 0.3 minus, whatever the value of t equals to 0.3 minus would have been the same for t equals to 0.3 plus, right? So we made use of that fact, got that from this equation. We got this, and the value we got was 5.276 volts. So then we solved for VCT, which we got the equation to be like this. Remember, every time that when you're falling from some point t naught, the value of that would come over here. It would be t minus t naught. So solve that for t equals to 0.8. We got 16.4. And since 16.39 was the closest, the answer is 16.39. So I hope there are no doubts up until now. So these are the questions that I wanted to discuss today. So let's go through whatever we did till now. So last week, as I told, we discussed first order circuits for source-free circuits for RC and RL. Then we discussed some singularity functions that were basically impulse, unit step, and ramp. Today we checked what a step response of an RC circuit would look like. So we took a voltage source with the unit step voltage source, which had the value 0 for t less than 0 and Vs for t greater than 0. We solved the circuit, and we used the concepts of differential equation, and we got that Vt was nothing but Vs, which was the voltage source value, and the initial plus and initial minus this voltage source value multiplied by, which is a decaying function of which is a decaying exponential function. Then we reached to an interesting conclusion that this could be represented as a steady state value plus a transient value, because this transient value is decaying with respect to t. So we broke those two into differences. That was a steady state voltage and a transient voltage. Then we came into an interesting conclusion that VCT could be simply be written as the steady state value plus the transient value, which is a decaying exponential function. Right. One more conclusion we reached was that it was VCT could also be interpreted as a natural response voltage of the natural response plus the forced response. Now, what is natural forced response? So here we use source-free equation, and here we use with source but without excitation. So initially it wasn't energization. At t less than t naught, right? So if you go through my last doubt clearing session or the last week's video lectures of the instructor, you would see for the source-free circuit, the equation would come out to be this, and for the with source circuit, the equation would come out to be this, where the capacitor was not previously excited. And if you further simplify the equation, you will find that it is the same thing that we derived today. Hence, there are two main conclusion, which are written over here, that can make your life easier while solving the voltage across the capacitor. Then we found the step response of an RC circuit with a current source. Here, instead of a voltage source, we were using a current source, and we used the conclusion that we derived previously and found the value of capacitor with a step response across a current source. Then we checked the step response of an RL circuit. We made use of the differential equation. Again, we solved for everything and came to a conclusion that it's nothing but the steady state value of the current plus initial minus steady state value, which is a decaying decaying exponential function with a time constant L by R. We rewrote the equation with the two conclusions. That is, it is a function of steady state plus a transient function, which can be written like this. You can also derive this for IT equals to natural response and forced response. Please try that yourself. You'll you'll get to you'll have a feel of how to derive these circuits. And then we solved some questions based on these interesting equations, right? And you could see that all of these circuits are very easy to solve and easy to manipulate. Okay, that's all for today. If there are any questions, I can take them right now. Okay, since there are no questions, I'm turning this off. I'll request everyone to please log off.
Hi, hello.
Yes, you're speaking. Yeah.
Yeah, I have one question. Can you give me one
Uh,
minute? I mean, I just noted down somewhere.
okay. Which question did you do?
Uh, the capacitor. Let me give me a minute. Let me. I just wrote it
Okay,
somewhere.
okay.
Okay, actually, I have a doubt. The capacitors, series. I mean, basically the CR circuit. Uh,
Mm-hmm. Mm-hmm.
like unlike capacitors parallel with voltage source, what if the capacitor series with voltage source and the resistor parallel with the voltage source? The behavior,
Okay.
I'm a bit confused actually, how charges are accumulated, the how the voltage divided.
Okay.
Can
So
you
you're saying
give me?
something like, yeah, just a second. So you're saying it's like this?
I don't see screen actually.
Oh, you don't? Oh, sorry.
I'm a bit confused about RC circuit versus the CR circuit.
And it's something like this?
No, the capacitor is series with the voltage source. The resistor is parallel, like CR.
Something like
Yes,
this?
yes.
So what's the difference between this and an RC circuit?
No, actually, I mean, if if we draw like this, there is no problem. Just, I mean, no difference. Just
Huh?
assume one terminal is there. Like, I mean, we are measuring the voltage in a terminal, another terminal, like the
Hmm.
parallel to the R. Uh, Assume like both are not serious.
Okay, so you can do one thing. I'm unable to gauge you properly, so you can talk to me in Hindi if you're comfortable more in that language.
No, not.
No, you're not. Okay, so what are you saying? So this capacitor terminal is connected to what? So,
Uh,
so, so can you please state your doubt clearly? So I'm unable to. So tell
okay,
what exactly your doubt is. Yeah. Hmm.
okay. But
Hmm. Hmm.
okay, I just take
Hmm.
the CR example only. I mean,
Hmm.
um, uh,
Hmm.
okay. First, I mean, if we have DC source connected with the particular C,
Hmm.
so after some time, C becomes uh, fully
Open.
charged, so the circuit will become open, right?
Mm-hmm.
Mm, in that case, what would be the voltage in C? I mean, voltage stored. It's
Okay,
equal to
okay, okay,
VDC.
okay. Yeah, yeah. Yeah, it would be VDC, right? Because it's an open circuit and whatever the voltage is across it is just
Okay,
simply VDC
right.
because no
Okay,
current is flowing.
okay. What would be the current? How to calculate current in the sense? I mean, IC current.
Current will
IC
be
should be the
current
I R.
IC would be zero, right? Since after, or let's say it reaches some T steady state, right? So the capacitor will become open circuited.
Then
So
IC.
no current will flow through it, right? It's an open circuit, so no
Okay.
current flow. So ICT will be zero.
Okay. Then IR also should be zero.
Yeah, yeah, IR will be zero. Yes. No, same current. It's a series circuit, right?
Zero. Okay. Then I missed my question actually. It's okay. Yeah. I'll.
So you can do one thing. You can do one thing. So you can write to me if you feel that you can remember the question anytime soon. I'll just write my email ID over here.
Okay.
Or once it's, or you can also comment on the comment box where this video will be uploaded. So I'll be able to better help you. So don't worry, don't hesitate when you are sending the question. I'm here to help you on this. Right?
Sure. Sure. Yeah. Thank
Yeah.
you.
Okay, no worries. Bye. See you in the next session, right?
Bye.
Okay, bye.